everyone, welcome back to NodeNotes. In today's lesson, we are going to learn about one of the most common ways to represent graphs in computer science, the adjacency list. Graphs are used everywhere, from social media platforms and navigation systems to computer networks and recommendation engines. Understanding how graphs are stored is an important step toward mastering data structures and algorithms. By the end of this video, you'll understand what an adjacency list is, why is it useful, how it compares to an adjacency matrix, and how to implement it in Java. Let's get started. Before we talk about adjacency list, let's first understand what a graph is. A graph is a data structure used to represent relationship between objects. A graph consists of two main components: vertices, also called nodes, which represent objects, and edges, which represent the connection between those objects. For an example, in a social network, people can be represented as vertices and friendships can be represented as edges. Graphs are widely used in many real-world applications, such as social networks, Google Maps, computer networks, and recommendation systems. Whenever we need model relationships, graphs are usually involved. Now that we know what a graph is, let's look at what the adjacency list is. An adjacency list is a way of representing a graph where every vertex stores a list of its neighboring vertices. In simple terms, each node keeps track of the nodes directly connected to it. Instead of storing every possible connection, we only store the connection that actually exists. This makes adjacency list very efficient, especially when a graph contains relatively few edges. That's why adjacency lists are commonly used in real-world applications. Let's look at a simple graph example. In this graph, we have vertices labeled as 1, 2, 3, 4, and 5. The edges are 1 is connected to 2, and 1 is also connected to 3. 2 is connected to 1, 2 connected to 5, 2 connected to 4, and 3 is connected to only 5, and lastly, 4 is connected to 5. Notice that every edge represents a relationship between two vertices. Our goal is to store these relationships efficiently using an adjacency list. One of the biggest advantages of adjacency list is memory efficiency. For a graph with V vertices and E edges, the memory requirement is O of V plus E. This means we only store each vertex once and only store edges that actually exist. Compare that to the other representations that may reserve memory for connections that don't even exist. This is especially useful for sparse graphs where the number of edges is much smaller than the maximum possible number of edges. In real-world systems, sparse graphs are extremely common, making adjacency list a practical choice. Now let's compare adjacency list with another graph representation called the adjacency matrix. An adjacency matrix can use a table or two-dimensional arrays to represent connections between vertices. Each cell contains either a 1 or a 0. A value of 1 means an edge exists, while 0 means no connection exists. The adjacency matrix allows us to check whether an edge exists very quickly. However, it requires much more memory because it stores information about every possible connection. On the other hand, adjacency lists only store existing connections, making them much more memory efficient. As a general rule, use adjacency list for sparse graphs and use adjacency matrices for dense graphs where many connections exist. Now let's see how we can implement an adjacency list in Java. We use a hash map where the key represents a vertex and the value represents a list of neighboring vertices. The constructor initializes the adjacency list. The addVertex method creates a new vertex, and the addEdge method creates a connection between two vertices. Because this is an undirected graph, we add each vertex to the other's neighbors list. This ensures the connection works both ways. Next, we create our graph inside the main method. First, we create a graph object. Then, we add the vertices A, B, C, and D. After that, we add the edges A to B, A to C, B to C, and B to D. At this point, we have successfully recreated the graph shown earlier in the presentation. The graph structure now exists in memory as an adjacency list. Now let's display the graph. The print graph method loops through every vertex in the hash map. For each vertex, it prints the vertex name followed by all its neighboring vertices. This allows us to visualize the adjacency list directly from our program. The nested loop goes through each neighbor and prints them one by one. This is a simple and effective way to see the graph structure. After running the program, we get the following output. A points to B and C, B points to A, C, and D, C points to A and B, D points to B. Notice how the output exactly matches the adjacency list representation we created earlier. This confirms that our graph has been stored correctly. Let's summarize the advantages. First, adjacency lists save memory because they only store existing edges. Second, they make it easy to add new vertices. Third, adding edges is straightforward. Fourth, graph traversal algorithms such as breadth-first search and depth-first search work very efficiently with adjacency lists. Finally, adjacency lists are ideal for sparse graphs, which are very common in practical applications. These benefits make adjacency list one of the most widely used graph representations. Although adjacency lists are powerful, they do have some disadvantages. Checking whether a specific edge exists may take longer because we may need to search through a list of neighbors. For beginners, adjacency matrices can sometimes feel easier to understand because they look like a simple table. Also, when graphs become very dense, adjacency lists may lose some of their memory advantages. For an example, if we want to know whether A is connected to D, we may need to search through A's neighbor list to find out. Let's look at some real-world applications. In a social network, each user can store a list of friends. That is essentially an adjacency list. Other applications include friend recommendation systems, navigation system, internet routing, and network topology management. Whenever we need to model relationships between connected entities, adjacency lists are often used behind the scenes. This is why graph representations are such an important topic in computer science. Let's quickly recap what we've learned today. A graph consists of vertices and edges. An adjacency list stores the neighbors of each vertices. It requires O of V plus E memory. It is highly efficient for sparse graphs. This is a small structure of how a sparse graph is, and it is widely used in many real-world systems. Understanding adjacency list is an important foundation for learning graphs algorithms such as BFS, DFS, shortest path algorithms, and many others. This is how adjacency list stores neighbors of each vertex. Vertex 1, the neighbors are 2 and 3. As you can see, 1 is connected to 2 and 3. Likewise, 2 is only connected to 1, 4, and 5. So the neighbors of 2 are 1, 4, and 5. 3 is only connected to 1 and 5, which makes the neighbors 1 and 5. And 4 is connected to 2 and 5, and the neighbors are 2 and 5. And 2, 3, and 4 are connected to vertex 5. Thank you so much for watching this NodeNotes lessons. I hope this video helped you understand graph representations and adjacency list more clearly. If you found this video useful, please like, share, and subscribe to support the channel. And don't forget to turn on notifications so you never miss a future lesson. Until next time, keep learning, keep coding, and keep growing. See you in the next video. Bye.